Our next talk addresses the challenge of extending the meta-theory of Scala's core type system. This talk will be presented by Paolo Giarrusso, and the paper is entitled Scala Step by Step, Soundness for Dot with Step-Indexed Logical Relations in Iris.
Hi everybody, and thanks for tuning in. Today, I'll present joint work with Leo Stefanesco, Amin Timani, Lars Pickett, and Robert Krebers, a new approach to soundness proofs for the dot calculus, the core of the Scala programming language. Before we dive into this talk, you might ask, what's interesting about the Scala type system? One might answer that Scala unifies functional and object-oriented programming, or has a very expressive module system. But what does that mean? In other functional programming languages, software modules are expressed through special constructs such as type classes or ML modules, which are not first class and require a special abstraction mechanism. Instead, Scala extends regular objects with abstract type members, allowing objects to serve as first class modules. Hence, you can instantiate modules at runtime and abstract code across modules using regular Scala abstraction mechanisms, such as plain functions or even mixing inheritance. While abstract types appear in other sound time systems, Scala abstract type members are a significant challenge to our type soundness proof because they gain impredicate type members, which are relative of type, colon type, and are challenging to prove sound. In a few slides, we will see a very small example. While Scala is interesting, its type soundness has been, in fact, an open question since Scala's introduction in 2003. Soundness proofs has been machine checked for significant Scala fragments, the dot calculus, an amazing success. However, we have no proofs that abstract types are indeed abstract. And dot calculi lag behind Scala even on core features and are not catching up. Dot is hard to extend, while Scala's evolution is not slowing down. To create a more extensible dot calculus, our approach is to avoid syntactic proofs that use preservation and progress. Instead, we build a logical relation models to prove type soundness and data abstraction. Then, we retrofitted a version of dot over this model, obtaining a more extensible dot variant called guarded dot or G dot. Unfortunately, guarded dot adds certain guardedness restrictions, but in our evaluation, it seems acceptable. In exchange, G dot is more extensible as we show through some additional features that we'll mention later. To make things concrete, let's now look at an example of Scala code. In this example, we create validator components that validate inputs from users. They provide an abstract type valid of valid inputs and a corresponding smart constructors make that validates its input and returns either valid data or nothing. Up to this point, nothing too fancy. However, new validators can be created at runtime, each with a distinct abstract type valid. To simplify the code, we had code the input type to be int, and we say that an input n is valid if it is greater than some constant k. The solution is in the next slide. Our solution is an object that defines a type of validators. Inhabitants of type validator contain two members: the type of valid inputs, valid, and the smart constructors make. Valid is declared to be a subtype of int, the type of all inputs. That is, type valid as int as upper bound, and implicitly, the empty type nothing as lower bound. These bounds encode that valid is abstract. Hence, inhabitants of valid can only be constructed through make. Function make validator maps input k to a validator that accepts only integers greater than k. For instance, here by calling make validator 0, we create a validator called pos, which only accepts positive integers, as shown by fails and walks. The type system rejects no because pos.valid is abstract, even though it is implemented by int, preventing users from bypassing our smart constructors. Thanks to first-class modules, we can also choose k at runtime, as done when creating legal ages. As promised, type legalages.valid is a distinct abstract type because legal ages is a different object with different validation conditions. This small example already uses many Scala features. So we see that in Scala, first-class modules with abstract types are encoded as objects with bounded type members. we have used the typing rule for type member introduction. A type definition type A equal T inhabits a bounded type declaration type A between bounds L and U if type T is indeed between bounds L and U. We have even used impredicative type members. Types like validator with nested type members like valid are still regular types, not large types in some sense, and are subject to regular abstractions. So for instance, validator can in turn be a type member. Next, we sketch how we prove type soundness. We'll oversimplify this talk and leave the rest to the paper. Our model uses a logical relation. That is, we map each type T to a set V of T of values that behave as required by type T. For instance, intersection types are interpreted using set intersection. The set V of S and T is the intersection of V of S and V of T. Then we map syntactic typing judgments to semantic typing judgments. For instance, S is a subtype of T if V of S is a subset of V of T. Crucially, an expression E, a semantic type T, if E runs safely and any result is in V of T. Hence, semantically typed expressions are type safe by definition. Then we map each typing rule to a type lemma about semantic typing judgments that we must prove. For instance, type S and T is a subtype of type S because V of S and T is a subset of V of S. We now have a type soundness proofs that is extensible. Proving new typing lemmas cannot invalidate all once because each lemma is proved independently. Next, we show a naive model of impredicative type members. We say that an object V has a type member A between bounds L and U if V dot A contains some type phi, which is indeed between those bounds L and U. Here, meta variables P and V range over sets of semantic types and values defined as follows. Types, a set of values represented as membership predicates, and values can be, among other things, objects, that is, finite maps from field labels to values or types. However, this definition is illegal, and because inlining some type shows that we're defining SemVal by negative recursion, which is illegal. This problem is exclusive to a setting where we have to model impredicative type members. Thankfully, abstract step indexing allows us to construct SemVal with a small change to our recursive equation. We must guard the recursion. That is, storing types into values must truncate types using the iris later functor. I won't explain what exactly that means, but we can ignore details and reason about the solution to this equation using the iris logic. Most of the logical relation will be identical to the naive model, except for type members. Since values only contain truncated type members, assertions about type members must be weakened using the later modality, as shown in this example. Here, a value V as type member A between L and U, if V dot A contains type phi, but later phi is between later L and later U. At this point, we can retrofit dot over this model, obtaining G dot. So we turn rules from P dot and upsilon dot into typing lemmas appropriate to the model. Each proof is around 2 to 10 lines of code. We add a type later T reflecting the later modality and associated typing rules. In this process, we obtain some stronger or additional rules. In other cases, the restrictions become more principal. For instance, abstract types are supported also in nested objects, as we have used in our example. We obtain distributivity of and or and other connectives, and we also obtain some typing for recursive types even beyond the typing used in the upsilon dot variable. Here we show a few selected typing rules. Rules subtype cell subtype show that selecting a type member A from path P, which is a certain type, which is a type member between L and U, gives us a type which is between later L and later U. This reflects guardedness restriction on type members. Next, ULT coerce shows how we can eliminate later in many cases by adding no coercion to terms. Next, ULT braces I allows introducing recursive objects. To prevent certain circular typing derivations, we avoid the ad hoc fixes of other dot calculi and guard against recursive self-references by adding later to the type of self-variable x. This rule says that to create an object with definition x and give it type mu_x dot object type mu_x dot t, we must check that the definitions may have type t in a context where the self-variable x has type later t. Finally, ULDVAL allows to nest objects inside other objects. Unlike in PDOT, nested objects support absolute type members. And this is possible because of the restriction we added to the rule for object introduction. In the paper, we give motivating examples for some of our novel features. We scale this model to G-dot, explaining how to deal with mu types, singleton types, path-dependent functions, full paths, and so on. We demonstrate expressivity despite the restrictions to type members. We give proofs about data abstractions, and we mechanize everything in Cork using Iris. And our soundness proof is of around 9,000 lines, and our examples take around 5,000 lines. For future work, we're extending our model to deal with type projections and higher kinds, additional scalar features which have not been supported by past dot calculi. We would like to find a way to elaborate two dot from calculi closer to Scala and to infer occurrences of later which Scala users currently do not have to write. And we hope that these techniques can be extended to other object-oriented type systems which support impredicative type members of virtual classes. In conclusion, Scala's type system calls for extensible type soundness proofs. So we design our type system using a semantics first approach. The challenge, or one of the challenges, was that impredicative type members are crucial for Scala's expressivity, but are hard to support. But luckily, using Iris enabled machine checking a solution in a convenient way in Cork. Thank you very much for your attention.
Thank you, Paolo. If you are watching this talk live as an ICFP participant, please look to see if there is a Q&A session available in your time band so that you can discuss this work with the author of the paper.